Merci. So, good morning everybody. I will speak in English, but I speak relatively slowly because it's not my mother tongue. So it looks for somebody who eventually could translate into. So we speak about nuclei structures, molybdenum and technetium cases. This presentation is a follow-up of the presentation I gave last year. Last year I gave a presentation which is, just a moment. For those who have this book, the presentation is page 124. Next page. You see several authors predict that alpha particle structures could be present in atomic nuclei. It's what I told last year and presented last year. I presented it for, let's say, N-alpha nuclei. Let's say it was like oxygen 16, carbon 40, carbon 20, etc. Today, I will try to apply it also to other nuclei, which are not, of course, N-alpha only, but which contain alphas, of course, but also other neutrons or protons. So according to my theory, it's a theory and it's an hypothesis, of course. The nuclei of the various elements are constituted with alpha particles, as I said, and other nucleons which are grouped in order to create some subnuclei linked by 4 types of bonds. I called, as is here, NN, NP, NNP, NPP. These binding energies, so these bonds, are that one of deuterium, which is NP, tritium, NNP, helium-3, NPP, and NN is another one I have found, I will just explain, and they are linked by these equations. Binding energy EB, the binding energy of tritium, let's say NNP, is equal to that. Same with helium-3 and 2NN forming a neutronic part of the binding energy of the alpha particle. This I demonstrated last year. If somebody is interested in more details, he could go on my website to have more details. So today it will be shown that this hypothesis of alpha structures in the nuclei can describe the binding energy systematics. In such an approach, the system works or is like a ground state behavior, like a crystal with stationary configuration and shape and with defined bond values between the various alpha particles and other subnuclei. And I give the examples, the following examples: molybdenum and technetium. So I developed that hypothesis, as I told, on my website, which is www.philiphat, like my name, .com. So for those who want details. Next page, please. The values I used are the following for alpha particle. So much math. EBNN I will just explain. The others are those who are listed in every book. Let's say for NP it's 2.22 meth, etc. 8.48, 7.72, something like that. So, and for EB alpha and EBNN, they are defined in my document on the internet. And the others are those are the newest documented values we have, it is IMA 2012. You see also some lines, these correspond to some lines. It's for me the facility for calculating. If you look, all these lines are interrelated, and I will, in the course of the presentation, I will tell you why, how. Also, we can say that NN and NP are always oscillating, and so I defined a binding energy A, which is EBNN plus EBNP divided by 2. Okay. To determine these lines, for the example of the deuterium, we take these 4 lines multiplied by the value of the electron, 0.511 MeV, multiplied by a conversion factor. This conversion factor is the same for everything and helps the calculation. So, 2 remarks before beginning. In my theory, binding energy of the nuclei has a unidimensional energy value. It's a value of energy, it's not a value of, let's say, a structure. I'm not demonstrating a structure of the nucleus. I'm looking for a distribution of the binding energy within the nucleus. This is something which is different, actually. Of course, it is related, and my work could be complementary to those dealing with this topic. So a comparison with 3D nuclei models could be relevant. What is the importance of that work according to me? It's important to know the distribution of the binding energy in each element at the beginning and at the end of the LNR fusion or transmutation reaction in order to follow the process, actually. This is the basis of my work, to see how the binding energy and the components of the binding energy are changing from one nucleus to the other. And I give the examples. Okay. What is that?
Что-то у тебя на экране, Сам, не пишешь.
Нет, этого не было.
It's in your presentation.
Oh God! Oh, sorry for that. It's a bit pity, but okay. I will try. I will try it. So these are the first 2 examples: molybdenum 92 and molybdenum 94. So one has, after my hypothesis, 21 alphas and 8 neutrons which are supplementary. There are 8 actually, you do not see, it's only 4, but the other 4 are here. And on 94 molybdenum, of course, they are 10, because there are 2 and supplementary more. You can see, perhaps not exactly what I wanted, but you can see that all the supplementary N are related or are bonded to the alpha with the same value, 2 A's, which is NN plus NP. In that case and in that case. And you can see that the relation between the alphas is always also an A link, an A bond each time. The only thing which is changing in isotope compared to another isotope is what is herein, you see. Here it's not only A, ideally it should be A, but it cannot be because it's not symmetric. Actually, in nuclei which are absolutely symmetric, it is the case. But as the majority of the nuclei are not symmetric, for instance here you have 21 alphas, this is not symmetric. So, and 8 or 10 supplementary N. So you cannot have this, this distribution. There is a little difference in the distribution, but when I apply all these, I find a binding energy which is very close to the value, experimental value, which is 14.25.81 MEF, you see. And the difference is very slight. So we can retain that within that part, which is a sort of, how to call that, a system to show the distribution of the binding energies. It has nothing to do with the structure, of course. You can see that there are 14 R, 3 NP, 1/2 NPP, and 1/2 NNP bonds. And this, as a total, is equal to the binding energy found after the experience. So next slide, hoping that's better. Next. Ah, yes.
That's next.
This is 95 MO and 96. So same remark. Here you have only A bonds. Here also. Between the alpha also A bonds. And here there are some slight differences. Here you have 17A, 1 NPP and 1/2 NNP, which gives at the end, compared to the experimental value, a difference of 10 keV. The same for 96, the difference is 13 keV. And we have 15A, 1 NN, 1 NNP, and 1 NNP. So it is practically the same, but there is a difference of 1 N, 1 neutron more in that nucleus, 96 compared to the nucleus 95. The only difference, according to my calculation and to my hypothesis, of course, always I say, is that there is inside this relation a little difference due to the less symmetry of the nucleus. So next page, please, slide. What's that? So here you have even a most interesting comparison. Sorry for that. It's Molybdenum 97 and Technetium 97, which is not the same as you know. So there is a little difference here. This is 98 now. Okay, let's take 97 and we will see afterwards. Sorry. So here you have 13 supplementary N, you see, which are here shown here. You have to imagine there are 13. And here you have only 12 and 1 proton. This is the difference in the structure. Because technetium 97 has 1 proton instead of 1 neutron supplementary to the alpha particles. There is a little difference in the distribution of the binding energy. Here you have 19A, 1 NP, 0.5 NNP, with that result. Here you have 17A, NPP, and 1/2 NNP bonds. With that result, is par hasard equal. So we can say that technetium 97 decays into molybdenum 97. Actually, it's electronic capture. The EB difference in bonding between these two elements is equal to NP divided by 2, let's say half the bond of a deuterium. You can see it here. If you had a half deuterium, which is 1 something 2, you have exactly this value. So, but this can be differentiated in the following thing. Here on the crown, I would say, there is a difference of NP divided by 4, because NNP is bonding is a bit more important than the 2A bonds. And the others have a difference, I cannot show it, have a difference on 3/4 of 3/4. Let's say at the end 2 lines or half the deuterium bond. You can see that it's really a very weak difference between the 2 nuclei. Very weak. Of course, there is a proton here and a neutron there, but in the total of the bonding, it's practically the same. Of course, this we knew before by experiment, but nobody, according to my knowledge, of course, nobody has shown that what is it really the difference. I tried an explanation. Of course, it's an explanation after my hypothesis. Maybe it's not the good one, but it's an explanation, and you can discuss about the explanation. So we can see here the electronic capture and the difference at the end of the binding energy explained, or let's say broken down after this system. Next slide. We are more lucky here. I don't know why. Here we have Molybdenum 98 and Technetium 98. You can see also the difference here. There is one N and here is one P instead, and the difference is also 16A here, 0.5 NN, 1 NNP, and 1 NDP, and here. Same. Again, the difference is very low. I can show you. I have calculated it. Just a moment. Yeah. Yeah, the difference is very low. It's equal to NP minus NNP, half NNP. Again, but here this one is stable or practically stable. Some are saying that it's decaying half-life 10, 18, how do you call that in English? Squared 18. It's very billions of years. It's not important. It's not important. And this one is decaying in ruthenium. This is not on the table because ruthenium I have not calculated for ruthenium. I have made the difference between molybdenum and technetium. But you can see also there is a very little difference between the 2 nuclei. Next page, please. This is 99, and this is very interesting. You have here molybdenum 99, which have a lifetime very short, 60 hours, 66 hours, something like that. And technetium 99. So molybdenum 99 decays beta minus into technetium 99. The EB difference between the 2 elements is equal to NP divided by 4, which is detailed as follows. You can see here you have 2A, and here you have an NPP bond because it's a proton, and this is a neutron. This is the difference. If you look here, there is no difference. No difference at all. 19A, 0.5 NN, 0.5 NNP. Actually, these 2 nuclei, which are different elements, have exactly the same bonding system, bonding dispersion or distribution. Sorry. This is the same. This is the same. This is the same with the exception of that one. Creating a new element very rapidly, and we say in 66 hours. The others, when they are decaying, take millions of years. And that one is have just a decay of 66 hours, let's say, because probably the difference is only due to the beta decay and not because of the strong force. Actually, it's only the weak force here, which is working. You see, the N is transforming into P. What is known, because the neutron is transforming in proton relatively easily. If a free neutron is a quarter of an hour, of course here it's longer, but not so much longer. And we can see the real lack of difference of the two nuclei, with values which are very close to that experimental value. Two curves here. Here it's a bit more, but of course we have not to forget that there is a decay, and of course this could modify a little bit the calculation of the experiment. This is a very, according to me, a very interesting view of two elements which are practically the same, and which decay only after the weak interaction and not the strong interaction. The other formally modified the binding energy herein, so it was a strong interaction. Here it's only a weak one. Next, this is just to finish molybdenum 100. You can see that now we have 16 supplementary ends, and practically everything is comparable to here. Actually, instead of having, ideally, as I said in the beginning, 21 A bonds, we have 20 A bonds and half an NP bond. For the rest is practically perfect. So this was a theory of molybdenum and technetium. Next. So here, this is a summary of the bonds value. You can here see the various elements or isotopes. The direct bonds, which are always 21A because there are 21 alphas, and the bonds for the supplementary N or P. As I showed you, there are some differences, so we can see this difference is, for instance, here the last one was 20A and half NNP. These are called transversal bonds. You see here the remarks and the conclusion. As for the direct bonds value, the transversal bonds value, these ones, should be ideally equal to 21A. It's not exactly the case. You see there is slight difference. The lines which should be at stake are these ones. We can see that molybdenum 98 and 100 values are a little bit higher. They are bigger than what is ideal. In case of molybdenum 100, it is obvious that if we transform that one in A, it is perfect. For the others, it's a bit more complicated, as I see here. we need some supplementary transformation. First remark. Then second remark, for molybdenum 92, 94, 95, it's slightly inferior to the standard. It's often the case if you have 6 or 7, as usually, isotopes. One are a little bit weaker, binding energy is a little bit weaker, and the others is a little bit stronger, but they always oscillate around the mean or the ideal one, which is that one. So some are higher, some a little bit less. The difference, meanwhile, is not important. For the first one, it's a bit more. But this is always the case. If you have isotopes, the first one is a bit, let's say, weaker. The others have differences of lines which are very, very few, equal to 1 deuterium bond. 1 deuterium bond on, let's say, hundreds of mass. It's not much. Another interesting point is that the comparison with Molybdenum and Technetium, we have seen the difference of the 99, which is very slight difference. For the others, we have seen also that there are some differences which are linked with a strong force and not with weak interaction, like for 99. So this was the presentation. It's if someone want to have more details for far more nuclei, there is a book here I have issued on internet. I have no editor, but I have internet. This book is also on the key. So Nikita, if you wish, you could download this book. It's called Livre because it's in French. Sorry, it's book. And other documents. So if some are interested to have more details on more nuclei or isotopes, they are here on this book or on other documents. So if you don't know everything, everybody could ask Nikita. It's better to ask Nikita than to ask me, because you can do it in Russian, of course. So thank you for your attention, and I'm ready for questions now.
А вот как ты по-английски,
Comparison your calculation results and experimental results have here some differences in your analysis.
As you see,
Very experimental.
yeah, I am.
Where you this is your calculation.
If you take another slide, maybe former slide, you can see. Yeah, okay. Here you have the experimental, which is determined by RMA 2012.
Ну вот разница, вот эти вот разница, вот эти 0,016.
Calculation.
This is calculation.
It's experimental.
This is experimental, and the difference is 16 kelvin.
My note for you. This letter you must make more size.
Не видно ни черта, короче.
I don't see.
We don't see. I see this not defect. Thank
But
you.
this is American and Chinese IME 2012. Everybody knows, you see, so okay, it's not to be discussed. I have taken my calculation, and of course, I fall on things which are very close.
Ну там вот минус вот эти Kelvin.
Yes, exactly, yeah. Yeah, you see, this is what I calculated, 44 61, and here it's 46, 26, so it's a difference.
16F.
Sorry? It's in KEF. Yes, of course it's in MEF, but this is in KEF.
My question for you. Now we have a community who study low energy nuclear reactions. And your advice for the experimental physicist, what's, according to your opinion, what's the best element for the low energy nuclear experiment, key low energy nuclear reaction experiment in future?
This is a very good question I will think about, because I have no.
No, this is, thank you, Anatoly. This is a very good question I will think about, because I do not really know. I am not an experimenter. This is my great difficulty, I may say. I am a theorist, so what I would like to do, to try to answer your question, is the following. I am working alone on that book. I have now determined hundreds of these nuclei, but there are 3,000, as you know. So basically I can do it, but I need some help. Because just for the calculation, it's too long for me to do it alone. You see, it's just you need time, you need okay, etc. So if I could, and this is a demand here to the Russian community, if I could have the help, let's say, of some Russian colleagues, we could work together per mail. It's not necessary to be in Russia, but if I could be, let's say, a few weeks in Russia or a few months in Russia, I do not ask for money, but if I could be there and work with 2 or 3 people in order to complete the work, it would be fantastic. And then I could answer really your question, Anatoly. Then if we have the 3,000, and again I say it's possible, within 6 months to 1 year, let's say.
Он больше веществ должен помогать, короче.
If this is possible, think about, because I'm not asking for money, I am retired and so. And then we could determine really which one is the best. This is possible, and I'm ready to come here or to work with you in any way.
Please, question.
Филипп,
Yeah, take the micro.
Вот сюда можно.
My voice is less loud. Maybe
Yeah.
I can. Thank you for your presentation. And as I understand your approach, it's a stationary approach.
Yes.
Stationary approach. But my previous experience and mainly results of this conference shift me to the understanding that the real transition from one situation in experimental fuel to another state of experimental fuel is the time-dependent phenomena, and
The
time-dependent
Yes.
phenomena, not a stationary state. Stationary state from one stationary state to another stationary state, time-dependent phenomena. Could you give could you tell something about transition from that stationary to another from your approach?
from your viewpoint.
Of course. No, you're quite right. First of all, you're right. It's stationary. It's static, I would say. But it's also there is some dynamic in it, because if you pass from molybdenum 99 to molybdenum 100, you add a neutron and you can see the difference. So there is a sort of dynamic, but it's true. It's not a dynamic in the sense of an experimenter, as you said. I fully agree with you. what hint I could give, I am also working at present, parallelly to that, on the how do you call that, dipolar magnetic moment. Dipolar magnetic moment of the excited nuclei and of the ground state nuclei, etc., etc. And I think that we could accelerate, if this is your question, we could accelerate actually the transition with activating, let's say, some electromagnetic devices. But you know that. With what I can say is that if we know the difference between the isotopes or the elements, we could perhaps better determine how much time we need to help to that transition or to accelerate that transition. Acceleration of the transition is very important for some nuclei which are excited, actually in all the nuclear wastage. If we could, for instance, determine, and I can determine it statically, as you say, stationary, determine the binding energy distribution of these nuclei, we can see maybe how to accelerate the, how do you put that in English, to go again to the ground state, you see. This is a possibility, but we have to see then. It's more work for me, and for me alone, it's a bit difficult because I'm not an experimenter. But I am.
Problem, Philip. Problem not in accelerating of transition. Problem is how to do transition from one point to another. Nuclear physics gives and shows us that transition generate a very high gamma X-ray radiation.
Yeah.
But we see in our experiment that this transition not generate such very high.
Okay.
And my question was how to move from one steady state to another steady state without gamma radiation. Is it possible?
It's possible.
From your approach?
It's possible. After my approach, it's possible. Yesterday we had a very good intervention by Uruskoev, who said we could add neutrons, basically. Add neutron to an element to create other isotopes, etc. So if my approach, you will see that on my blog, on my website. It is about, let's say, the structure of the neutron and the proton. I have, all this is based on my own, how do you call that, structure, yes, of the neutron and the proton, which is different to that one which is presently accepted. And so if you look at that, but of course it's an hypothesis, if you look at that, you can see some possibilities to change that. Because for me, I have nothing to write. For me, actually, a nucleus has a lot of stationary phases behind, which are hidden. And when there is how you call that, interaction between two nuclei, a nuclear interaction between two nuclei, what happens? This, what is behind the both of the nuclei, is disturbed. And it's the reason why we see so many neutrons or so many gamma rays, etc., which is more or less the same. Let's say it's just another way. The gamma rays are electrons and positrons, etc., which are merged. A neutron is different. So this is my theory about the neutron and the proton. If you have you can have a look on my website. So here we can see how to escape that problem. Of course, theoretically, because I am not an experimenter. But one is sure, the neutron has a lot of hidden mass behind the present mass, and also a hidden antimass. Because to create the mass of a neutron or an electron in our present space-time, we need much more energy than what we see in our space-time. And this energy is hidden by antimass. This mass was created and then annihilated, created.
Philip, this is new presentation. you answer on my question. Thank you.
You should look at my website. I'm ready to speak together.
Short question.
Yeah.
Can your analysis help us to understand a native relation between isotopes, between stable isotopes? You can predict the native relation between isotopes, molybdenum and other. Yes? And where I hear this your results on the exist?
Отдельного нейтрона, а поглощение каких-то маленьких квантов.
Есть вот квадрофорное взаимодействие, так называемое, которое, так сказать...
Just a moment.
Но все равно он сказал,
After your...
ниже статьев ничего нет.
Dmitry, after your very interesting question, I offer you the book. So this book is also on my key. So for those who are interested, but I have not brought a lot because it's heavy. Your question is quite easy. Here we have seen the different kinds, the different isotopes of molybdenum. I can do exactly the same type of work for the other isotopes. You will see in the book the isotope of oxygen, even oxygen 17. I have nothing to write here, but I can give you a very rapid. If you have a bit time.
But this relation isotopes is different from Earth and Sun and other galactics maybe.
This has to be examined because I work a bit in isolation. I work as a terrorist, not a terrorist, a terrorist. And it would be interesting if we had more relationships to see your results, let's say what you have found in the cosmos, and my results.
And level also.
And Eliana, yeah?
You are isotopes, other relations between isotopes.
Exactly.
And you can predict this new relation.
Yes.
Well,
Thank you.
Порядка 5-6. А если изъявить как течение?